they move apart, making this part of the substance less dense and causing it to rise. So whenever we heat the particles, they tend to move apart from each other, and this makes the part of the substance less dense, which causes it to rise. This sets up what we call a convection current, and convection current is a term that's used a lot in the exam papers. Experiments that you will have seen in the classroom to show this, they include the potassium permanganate in water. When we put a crystal of potassium permanganate in the bottom of a beaker of water and we heat it, we can see the purple vapours rising up through the liquid, the water, due to the convection current that is set up as the warmer water particles rise to the top of the beaker. The burning candle. If we have a burning candle within a box and we allow some smoke to come in one tube, we'll find that the burning candle will create the convection current that carries it out the other side of the box. An experiment, whenever we see this one, replicates the potassium permanganate. Potassium permanganate is put in simply because it's purple and it shows us the movement of the particles. If we heat, then we can see the particles that pick up the purple dye. As they heat, they become less dense and rise, and they push up towards the surface. This then encourages the cooler water to sink down the sides of the beaker to move round to where it gets heated and then rises, and this sets up a continuous convection current as long as you continue to heat. The same applies to a gas. Onshore and offshore breezes. Okay, during the day, whenever the sun is shining, the land heats up, and this causes the warm air to rise off the land. We feel an onshore breeze if we're at the coast, because as that warm air rises, cold air comes in from the sea, from above the sea, comes in to replace that warm air that has risen due to its heating. It then gets heated, rises again, and the cold air keeps replacing it. So we have a continuous onshore breeze created by that continuous convection current. At night time, the reverse process happens. The land cools down very quickly, but the sea doesn't cool as quickly, so we have what's called an offshore breeze. Radiation then. Radiation happens in gases and in a vacuum. Heat is transferred in the form of a wave from hot objects. So hot objects give off radiation as a wave. The hotter an object is, the more heat waves it gives out. This is the only type of heat transfer through a vacuum. The other heat transfer requires molecules. Remember that conduction can be transferred via the molecules vibrating and touching each other and collisions of the molecules that are very close together, or by the free electrons travelling through it. Convection involves the movement of the molecules throughout the fluid, but radiation doesn't need molecules, it's a wave, so it can transfer through a vacuum. Evidence for the fact that it transfers through a vacuum is the fact that we feel the heat from the sun, and between the Earth's atmosphere and the sun is space, which is a vacuum, but yet we still feel the heat. Therefore, the radiation waves can travel through a vacuum. When we discuss radiation, we refer to absorbers and emitters. Absorbers are materials that absorb radiation or take in radiation, and emitters are those materials or objects which give out radiation. Black surfaces are good absorbers and emitters of radiation. Matte black surfaces are the best absorbers and emitters of radiation. Silver and shiny surfaces are poor absorbers and emitters of radiation. We often say that they're good reflectors. On a sunny day, if we had two cars, a black car and a silver car, on a very warm sunny day, if both were parked in a car park and you get into the silver car, you would find that it was cooler than the interior of the black car. Due to this absorption, the black car will absorb the sun's heat and radiation more than the silver car. The silver car will tend to reflect the sun's radiation away from the car. In class, we compared emitters using Leslie's cube. Leslie's cube is a cube which has the 4 side surfaces covered in different types of surfaces. We had a dark matte surface, a dark shiny surface, a dark matte surface, a dark shiny surface, a light matte surface and a light shiny surface. If we were to compare the emitters by measuring the heat given off at the dark matte surface and the light shiny surface, we would see the dark matte surface gives off the most heat and the light shiny surface gives off the least, bearing in mind that both surfaces are at the same temperature because both are touching the same hot water that is at the same temperature. Therefore, the surfaces themselves are the same temperature, yet the dark matte surface gives out the most heat. Similarly, we did an experiment to compare absorbers. We had the inside surface of each of the sheets was placed beside a Bunsen burner. One was painted a dark matte colour, the other was a light, shiny, polished surface. Both were set at the same distance from the heat source, and they had a drawing pin stuck on the outside with either wax or, in some cases, Vaseline. The Bunsen burner was lit, and we compared the time it took for the drawing pin to fall off each of the sheets, and we would find that the drawing pin fell off the surface with the dark matte surface most quickly, and the one that had the light